one question was about this empty set, which I think actually gives a problem to many of you. So I have decided just to pose a question as an exercise of finding some maps from set B to A, where we write this notation A to the power B. This is a very standard notation in universal algebra as well as in category theory. And Cartesian product is very much well known to all of us since our undergraduate set theory or abstract algebra module. So the first two exercises is just to warm up, and the last two is actually the problem what we experienced yesterday. So I suggest that if you get time, just to try to do this simple exercise, and the solution, obviously it's an exercise at this stage, but you have roughly 6 months to do this exercise, because there is no rush. This is not an examination or getting some job. So take your time and try to convince yourself completely that you have the correct answer with the correct reasoning. And you are most welcome to send me your work, and we can always discuss. At the end of today's talk, I will give you my email address. So with this remark, the other one was a question about functions. And let me give you an example which apparently doesn't look like a function when we studied our set theory or abstract algebra, but can we represent it as a function? Okay, so this is a question. X is an element of a set X, and this is a very, very standard thing. Whatever the area of mathematics we do, doesn't matter, this will inevitably will appear. Now the question is, can we represent it as a map or a function? Okay, so this is very important from this universal algebra point of view as well as from category theory point of view, because one of the purpose of category theory or the philosophy of category theory or the underlying message of a category theory is that objects are not only important, the maps between objects are also important. If not, they are more important than objects. And this has been actually been realized again and again after the discovery of category theory, in not only in category theory itself, but in other areas of mathematics like differential geometry, like algebraic geometry, commutative algebra, homotopy type theory, motives, and other places. So let us take this simple example. So what does it mean by that X belongs to X? Okay, probably it means like this. X belongs to X means we selecting or picking up a specific element from this set X. That's what does it mean by, because we wanted to choose somebody and we call that somebody as X. So this is nothing but representing or choosing an element from X which can be represented as a function from a singleton set to X. And that singleton set can contain any element. So I just put it as a star. We can put any 1, 2, 3, 4, or doesn't matter. Now, let us see this trivial map. What this trivial map actually doing? Since it's a function or map, this star should be mapped with exactly one point of the set X. And we define this map in such a way that this star will be mapped to X. And this trivial example of representations of X belongs to the set X has immense use or applications in abstract algebra, when you see algebra as a subject of algebraic structures. So keeping this in mind, that some of the facts which we didn't see as a map can also be represented as a map is actually a very good idea. It actually broadened our view about mathematics and its applicability as well. So now let us resume our usual discussions. So we will now revisit groups once again. Now you are thinking, how many times we will see these groups? Yes, group is a very, very interesting object, and it has so many applications that it's needless to say that one of the most useful algebraic structures in mathematics. So far what we have done these generalizations of getting this abstract definition of group from concrete groups, examples like R plus, complex number with addition, integers with multiplications. From there, we extracted information, and then we got a set G over some binary operations satisfying some properties, and we say that, okay, this is the definition of a group as an abstract object, as an algebraic structure, and of which all those previous entities become the examples in a concrete sense. But group also appears very naturally in other branches of mathematics, not only in abstract algebra. Definitely, it appears as a group. Then there is a special type of group, Abelian group or commutative group, that also appears in abstract algebra. But we have also topological groups, which is a very, very well-known area of research. There is a very nice book written, still considered as a classic by Pontryagin. Maybe you like to have a look if you are interested in topological groups, but there are also others. And then Lie groups. This is also a group, which is in another area of mathematics. Then in algebraic geometry related objects, we get algebraic groups. Now, wait a minute, we are confused. Up to yesterday, we had abstract group, and then we have concrete examples. And each of these concrete examples can be captured by this definition of abstract group, and you can say, well, these are examples of groups. Now, here, this word group is appearing attached with some other types of mathematical objects, or even different types of mathematical structures. So now it's a general question, then who is this group is actually a group? Is the first one is a group, or the last one is a group, or is a topological group is a group? Because we are saying all of them are group. So it actually tells us that, do we really finished with the definition of group as far as the abstractness is concerned? Probably not, because here group, when we take set theory, we got group or Abelian group. When we take topological space, we have another type of group, which is called group, topological group. When you have differentiable manifolds, we have another type of group, which is called Lie group. When you have algebraic varieties or affine schemes in algebraic geometry, then you have another type of group, which is called algebraic group. So who is this group then? Okay. So to understand and to unify all these different types of groups appearing related with different mathematical structures, let us see, or rather go back to our undergraduate abstract algebra and see the definition of group. Okay, this is the standard definition, what we see in every textbook in abstract algebra. A group is a set with a binary operation. We denote it by this product relation or addition, depends on, it doesn't matter, such that this binary operation is associative. Then there exists a strange element called identity, such that it satisfies this property that when you multiply in the sense of this binary operation, on the left, on the right, we get back the original element with whom we multiplied this special element, which we call identity element. And then finally, for every element A, with respect to this identity element, this is very important. If we change our identity element, inverse will also change, as we know with some standard exercises in abstract algebra. So we should mention E as well. For every element, there exists another element from the group or from the set, such that when you do this operation on the left-hand side or on the right-hand side, we get back this identity. And perhaps...
Amartya, if you kindly scroll down your slide.
Yes. I think it's, let's go like this way. Yeah.
Yes.
Yeah, sure. Thank you, Abhishek. So this is the standard definition. And we have seen this definition so many times that it is unforgettable. We cannot forget this definition. But look, there is something very strange about this definition. We started with a set with a binary operation, then number 2 and number 3 is not anything related with a map, but picking up some specific elements of the set, from the set. Can we not represent the definition of a group just using maps? And these maps will have some properties. And maps will be from G to G, just like this binary operation, which is just a map. And then it satisfies the property of associativity. But strangely enough, this number 2 and number 3 is not represented like as a map that the first one is represented. The property is represented of a map, the associativity of a map. So this question of writing an algebraic structure in terms of maps having an underlying set is not quite well known, or we do not see it often in abstract algebra book. Because if we ask this question, then the natural question is, wait a minute, what is the definition of an algebraic structure? Just like we have seen what is the definition of a mathematical structure, it's called a category and it has a very simple definitions. But hardly or strangely enough, when we study abstract algebra, in general, books talks about groups, ring, fields, modules, k-algebras, multilinear algebras, other algebraic structures, lattices, Boolean algebras, heading algebras, many other vector spaces. All these are algebraic structures. But remember, these are examples of algebraic structures. And each of these has their own definitions, and we study and they study their properties. But what is the definition of an algebraic structure? And that hardly we see. And that actually motivates us to understand this question that representing an algebraic structures as a set and a bunch of operations. So let us see what is this algebraic structure actually. So this is the standard definition of an algebraic structure. I'm sure you are utterly confused of these notations and it's so complicated. Yes, I completely agree with you. When you read for first time, it looks terrible and it's very complicated. But if we just pay a little bit more attention and pay some time here, and then it will be much easier to understand. And why this is so complicated? Because it actually caters for all algebraic structures. And this is the most formal way how we can define an algebraic structure. So let us summarize what is written here, and then we take an example and simplify this definition for the working purpose. So it is telling that we must have a set A, which is written here. And then we will have a bunch of operations, which we call this signature. And this bunch actually written in terms of these inverse images of this natural number. So corresponding to each natural number, by the way, natural number means starts from 0, not from 1, because there is a set theoretic reason for this, that natural number should start from 0. So for each of these natural number, take the inverse image and collect how many operations are there for each of these natural numbers. So basically, when you take this binary operation on this group, it is actually taking the values of only one binary operations for n equal to 2. And that gives here. So instead of going to detailed analysis of this definition, let us take an example how to use this definition with respect to this group structure. So for group structure, this omega n will be this collection. What does it mean? Okay. We take, let's start with m because that's the operation which appears naturally there. So it is our binary operation. So for n equal to 2, what does it mean by n equal to 2? It means g cross g. So g cross g to g. So for n equal to 2, we have exactly one operation, one binary operations, and that's why we have this and singleton set, and we wrote this operation as m. Now, who are these two people? Now let's go to n equal to 0. You remember at the very big first slide of today's discussion, we talked about that anything belongs to a set can be represented as an operation from a singleton set to that set. Now, existence of an identity element is nothing but picking up element, called it E, from the set G. So of course, we can represent it as an operation, as we mentioned before, as this from singleton set to the set G, and we pick up whom? We pick up E. So exactly one operation is there for n equal to 0. So that means for n equal to 0, this operation is called nullary operation. Okay, so that look after of this existence of identity in form of a map or operation. Which operation? Nullary operation. But there was another person. For every element A, there exists an element which is called inverse of it. So now look, if we just go back to this definition of this inverse element, so what it is doing, for every element A, there exists an element A inverse. So basically, this is nothing but a map from G to G. So whenever we pick up an element from G, we pick up another element from G such that it will satisfy this property. So basically, this existence of inverse is nothing but a unary operation. Unary in the sense when your n equal to 1. When n equal to 0, that's nullary operation that look after of this identity element. So if we take these three together, then essentially now we reformulated our known definition of group only in terms of a set G and three different operations. One nullary operation to look after of the identity element, one unary operation to look after this operation of inverse, and this usual binary operation to have this associative property. But this definition of algebraic structure is supposed to look after for all integers. So we take for n greater than 2, it's an empty. So there is no other operations we attach for this algebraic structure for group. And this definition is absolutely standard in the context of universal algebra. And if we open universal algebra books, we see these definitions. So if we study abstract algebra not in forms of group ring fields and modules, but if we study abstract algebra as study of algebraic structures, then inevitably this definition must or should appear there. Okay, so far we managed to change this picking up elements by some operations, specifically nullary operation and unary operations. But what about these properties of this nullary operation and unary operations? Okay, so can you further develop it? Okay, we can. And so it will be like this. So far we have a set G, a binary operation, a nullary operation, and unary operation. So E gives the corresponding identity element, I gives corresponding this universe elements. And what is happening? G is a set, that is true. And then M is a binary operation. Now, what I wrote on the right hand side in red color is the textbook version of the definition of group. What I wrote on the left hand side is the version to write it in terms of maps. So let us just explain one of them and the others will follow similarly. So when we say this binary operation M is associative, what we do? First, we take this operation between B and C. Okay, good. So just consider, Abhishek, is the cursor is also visible?
Hello?
Hello, is my,
yes.
Yes. Okay, good. Okay, so when we have this BC, how we got BC? We actually pick up an element B, we pick up an element C, we apply M, and that new element, we denote it by BC as an element of G. So this is nothing but this operation, M of B of C. Okay, good. So we got BC. And then we apply A. So now this new element BC is an element of, again, G, and then we pick up another separate element, which is A, and then we apply again this binary operation. So that second M comes here. So this left-hand side of this equality, of these left expressions, is nothing but this left expression, what we have seen. And similarly, first we compose, first we take these binary operations between A and B, and that's why we have MAB. Once we done that, we got AB as a resultant of this operation. And then we pick up another element C, and then we do the operation between new element, which is MAB or AB, and then apply C, and that we got M. So this is the way how we represent this whole operations just in terms of these map binary operations. And once we have that, next we got this nullary operation, which will look after of this identity property. So since it is picking up of an element, I denote the same symbol E to denote the map as the element of it. So star will be mapped to E. So E of star is the identity element. Okay, now go back again. So we just write it by the E. So E of star is represent the same symbol. Just so there are too many same symbols here. The function is also denoted by E, and E of star will be also denoted by E in this sense. So we take this image of it, apply A, and then to apply that, we need M. So you see, if we write like this way, we can literally see how these different operations actually interact with each other to express the properties of this identity, this associativity, and finally for this inverse property. And for inverse, it's a unary operation. So we pick up any element. I of A is nothing but our this notational symbol of A inverse. And when we apply A inverse with A, how to apply that? Again, we need these binary operations. Good. So far what we obtained. So far we obtained that a group can be defined as a set with three operations, nullity, binary, and unary, satisfying these four properties, three properties, and all of them can be represented like this. But remember one thing, that we started this discussion to talk about different types of groups appearing in different mathematical structures. So can we further simplify this definition or make it more abstract, in the sense that we can completely ignore in which mathematical structure we are, but still talk about these properties of group? What I wanted to mean here, that when we talk about the normal group, we do this so-called group structure on sets. But when we talk about topological group, it's not anymore group structure on set, but it's a group structure on a topological space. Similarly, when we talk about Lie group, what is it? It's nothing but a group structure on another mathematical structure, which is a differentiable manifold or the smooth manifold. So there is, now we understand, something called group structure, and that we put on different mathematical structure, and we get a representation of it in the form of group or topological group or Lie group. So this word group structure actually tells us that, okay, we need further distillation of this process of abstraction, such that we can capture or unify all these different types of groups in one language. So let's see how to do that. So that's why we need this mathematical structure. Again, as I said, if you feel uncomfortable with the word category, replace it with a mathematical structure. So C is a mathematical structure. It must have two properties. It must have a terminal object, and it must have a product. Without this, we cannot talk about the group structure on it. So now you see the difference is, there is no set. It's any mathematical structure having these two properties, or these two components should be there. Then this group structure, which is standard way of calling as internal group or group object in this category, consists of again the quadruple, the same G, but G is not anymore a set. It's an object of this mathematical structure C. And you see how much flexibility now we got. We can put G as a set, we can put G as a topological space, we can put G as a smooth manifold. And what property should it satisfy? Now this M, E, I are not functions in the form of a set. It's just a morphism. Which morphisms? Depends on which mathematical structure we are talking about. So for example, if we take this G as a topological space, then M will be a continuous map. If we take this G as a smooth manifold, then it should satisfy the smooth manifold preserving property. So this is the way how we can actually reinterpret, and it becomes independent of the structure. Okay, so far we have all the ingredients what we need to have this group structure. And similar way, we must now have the properties to be defined. So these properties will be represented by these diagrams. Okay, again, these diagrams looks a little bit strange, but if we just pay a little bit attention, then it is not very hard to understand. So just let us explain this first one. So we said M is this binary operation. So what is actually a binary operation? Binary operation is actually, first we start with three elements, A, B, C. So that is the Cartesian product. And this Cartesian product, again, G can be anything. I mean, it can be, say, it can be topological spaces, so there is no restriction on it. So we take three elements from this. So A, B, C. Now we pair it two at a time, because binary means we should pair them at a time. So first, if we pair the first two and keep the other as an identity, so there is no change. So basically, if we have A, B, C, I would have written all this here, that would be easier, but I hope you are following it. If we take A, B, C, and if we apply this binary operation between A and B, then you see we got here AB, comma, C, which is an element here. Then we apply again M. So M is now applying on AB, of, and C. So we got AB bracket and then C here. So this is one side of this associativity. The other side, okay, so we just fix the other way. So first we take this first component as an identity. So there is no change of this element of the Cartesian product. So we take A separate and then B, C together. So when we apply B, C together with M, we got BC as a product element type of notation. And here we have A comma BC, and then we apply M, we got exactly A times bracket BC. So that's exactly how we express this property of associativity of these binary operations. So this is the diagrammatic representations of group as a group object in a category having a product and terminal object. So this, once we have this definition, now we can immediately see all these different types of groups are nothing but realizations of this diagrammatic picture in different mathematical contexts. So now we have this almost obvious interpretations of the list. So now we pick up a category and we talk about the group objects in that category. So if we take set, then the corresponding group structure will be the usual group. Very interestingly, if we take our category as itself a group, then we can define a group structure on a group in that sense, having this property. And that will be interestingly abelian groups. So abelian groups are nothing but the internal groups in this mathematical structure of group. And group is nothing but the group internal groups in the category of or mathematical structure of sets. Next, if we take the category of topological spaces, the corresponding group object or the internal group will be the topological groups. And similarly, if we have the smooth manifold, we get corresponding Lie groups. And if we take algebraic variety specifically, or we can further generalize it taking affine scheme, then we get corresponding algebraic groups. So this is one way to tell you that how this representation or categorical interpretation help us to understand what actually we are dealing with and where we are. So if I am getting very emotional, then I consider this like a spirit and the body. You put in different body and then you realize it, something like that. So this group object or internal group is actually a structure, and it is not true that you can only put that structure on sets. You can put that same structure in other mathematical structure and realize it inside that mathematical structure. Okay, so this is one of the examples of the categories applications in unifications. The next important thing which appears in category theory is called adjunctions. So what is an adjunction? Adjunction is nothing but a pair of maps going in opposite directions. So that's like first example, we see direct and inverse images of a set. So if you have two sets, we take subsets, we can take the direct image of a subset, and we take a subset of the codomain set and take the inverse image of it, and then we get a subset on the domain side. So this is actually a pair of maps of in the forward direction and in the backward direction. So we have seen such examples, but these are not only a pair of maps, but they satisfy some beautiful properties, and many of the different situations or the constructions or the notions appearing in different areas of mathematics actually can pull together, and we can talk all of them in one language and can express in one language and simplify our constructional difficulties. Of course, we need to construct to get such things, but once we have the construction is done, we do not need to refer it back again and again whenever we wanted to use that concept itself. So the second is the free group. Free group is a very, very important concept, and that's very much related between this mathematical structure of group and the mathematical structure of set. For each group, we can actually get something free group from this. Next, polynomial rings, which is appearing both in ring theory as well in commutative algebra, as well as in algebraic geometry, and of course in other places. So these things we have seen again and again, but all of them have some these common properties, and this common property is that all of them can be constructed by using this concept of adjunctions, which we will define formally. Next is Abelianization. If our group is not very good, then we can make it good to construct an abelian group out of it. After that, something from topology, Stonecheck compactifications. If I remember correctly, this is a standard section from general topology, and at the MSc level, most of us have actually encountered Stonecheck compactifications. Of course, there is a branch of mathematics where we do research. It's called rings of continuous functions, where the Stonecheck compactification has very special attentions, and there is ultra-filtered way of constructions of these Stonecheck compactifications. But here we can look at Stonecheck compactification as a pair of maps and see how it comes inevitable way. So once we have all these things, now let's take okay, another one, Grothendieck group. It actually appears naturally in the context of K theory. That's where Grothendieck actually need to introduce this certain type of group, and we will see what is this group is actually all about. So this is a very important tool in the context of K theory. So let us take an example. Take the first one, that what type of relations is happening between these two maps. So if we take two sets U and V, then we take the power sets of U, and that actually forms a pre-order with this inclusion, subset inclusion relation. And then if we take this forward image, which we denoted by this F suffix star, and for the inverse image, we denote it F this superscript star. So that is nothing but going in the forward direction and going in the backward direction. And now we have seen yesterday that this power set is actually a functor from sets to sets. So definitely this forms a functor, but it actually have a little bit more properties, which is very important. And we have seen these two properties, what is written on this last line, as a standard exercise in our set theory. So what these two properties is saying that if we take first the inverse image and then the direct image, that will be contained in the original set. But if we do the other way around, if we take first the direct image and then the inverse image, then the original set will be contained in this process. But this is not an it's not an arbitrary incidence is happening only in this case of direct image of inverse image. Exactly this similar property, maybe not in the same notation, but in a different notation in another mathematical structure, is happening in all these cases what is listed up here. So that's actually give birth of this concept of adjunctions. This actually been discovered by Daniel Kahn, and around 1960s, in the decade of 60s. So let us see what is these adjunctions. And please do not be scared with these notational things, because you are seeing it for the first time. So let us try to understand what is it all about. Okay, so adjunction, as we said, that there should be two maps, and since it's between two categories, these two maps should be functors. So one functor is from X to A, and the other functor should go in the other direction. So it should be from A to X. And then there should be two more maps, and these two maps, if we see carefully, it's actually between the functors. So F is a functor, U is a functor, their composition is a functor, and 1x is actually identity functor. So this eta and this epsilon is actually two functors, and they have their names. I will just write down details as a picture. What is the definition of this natural transformation? So natural transformation is nothing but a map between functors, and functors are mapped between categories, and morphisms are maps between objects of a category. So these are the three different levels of abstractions or generalizations with respect to the different entities of mathematics. So once we have to these opposite directions functors, and they satisfy some kind of commutative diagrams, which is written like this way. And once we have these two properties with respect to these two functors, then we call F is a left adjoint of U, and U is a right adjoint of F. And this left and right adjoint are very, very standard terminology in category theory, as well as it has lots of applications in different areas of mathematics. Some of them actually we just listed in the previous slide. So after this, as we said that, let just quickly say that we mentioned that this eta and epsilon are natural transformations. So generally we wanted to know what are the natural transformations. So natural transformation is nothing but the maps between functors. So we take two functors between two categories or two mathematical structures, and then we wanted to define a map between these functors. So to define a map between these two functors, we must pick up an object, otherwise we cannot define it. It is very much same like that when we say two functions in the usual sense of set theory, f and g are equal. What does it mean? It's equal at each point. So fx equal to fy, fx equal to gx. If it is happening for all x, then we say f and g are equal. So exactly in the same token, we can actually tell that this definition of natural transformation actually we define taking an object, and then we define for each object, we have this map between FA and GA. So definitely we understand FA and GA is actually a map, or rather a morphism in this category B. Why? Because A was in A, and this A is of course in A. When we apply FA, it's a functor. So each FA should be an object here, and GA should be also an object here. And between two objects, we have a morphism. So FA to GA, this tau A is nothing but a morphisms in this category. Similarly, when you have this FA prime and GA prime, this is again a morphisms in this category B. And then we have this image map, the functor not only look after our objects, but also look after our morphisms. So now look, this F is a morphisms in this mathematical structure A. So its image should be a morphism in this category B. So that's why F of small f is nothing but a morphisms on this, and similarly on this side. So this is the definitions of natural transformations, which we actually use in the definition of this adjunctions. So now let us see how those examples we listed actually gives tells about this adjunction. So this free group. So what is a free group? First, we take a functor from group to set, and it's called forgetful functor. Why is it called forgetful functor? Okay. What it forgets? It forgets the group structure. So it's not a very, very efficient person, but it's very important person. So let me repeat, what does it mean by forget? Group has, as you remember, it has a set, G, and a structure. So set is there. Now this functor only carries the set on this side, and forget about the structure because set doesn't have any structure. So when you take this G, M, E, I, and when we apply this calligraphic G on that structure, here we landed up with only G. That M, E, I all gone, because that was the part of the structure, because here we can just get C. So this is the standard forgetful functor. We take any mathematical structure, forget some of the structure, may not be forget everything. We can take topological spaces here, mathematical structure, category of topological spaces, and we can similarly define a set. What do we forget? We forget the topology, because every topological space is a pair, x and tau. That's the standard notation. So when you define a functor from x tau to set, what we forget? We forget tau, because that's a structure on the set, and that gives a topological space. So this is a very standard way to forget structure and landed up with the underlying set. Good. So this functor has a left adjoint. That means there is a functor from set to go back here. And that's exactly is the free group construction from a set to a group. So we actual procedure of the free group is actually concatenations. We take these symbols as words, then we cancel each other. It's a standard procedure of construction, which you can find it in any abstract algebra book. But this type of representation is actually tells that for each set, once we have this forgetful functor, we can actually construct another other way around, and that gives us this usual concept of free group. And so free group is nothing but the left adjoint of this forgetful functor. Another very simple example, and which we do not see, that if we take a module and if we have this forgetful functor from this module to set, then actually if you take this free of version of it, then that is nothing but our vector spaces. So it is although in general in linear algebra we do not see this study of modules, it appears generally later on as an algebraic structure, but this concept of modules and this concept of vector spaces are very, very much interrelated if we see from this point of view. And of course we understand that when we talk about vector spaces, we talk about over a field. And if we just keep the same axioms of to define a vector space and replace this field by a ring, commutative ring. That's nothing but actually we get this module. So once we have this example, then another one is abelian adjunctions. So again, we take this inclusion functor. Inclusion because every abelian group is a group, so it's actually embedded inside it. So in that sense, it's inclusion. And if we take a map from group to back, and how to do this, this construction is the standard way of the subgroup commutator. Again, this is a standard material, what we can see in abstract algebra book. If I remember correctly, at least in the book of Serge Lang, and if I'm not very much wrong, I think Damit and Foot has also this detailed construction. So you can always have a look on that. But this construction is nothing but another example of these adjunctions between this abelian group to group, and abelian adjunction is nothing but the left adjoint of it. Next is our Stromcheck compactifications. So who is this Stromcheck compactification? We take this category of compact Hofstra spaces. So this is actually a subcategory of this category of topological spaces, because every compact Hofstra spaces, of course, is a topological space. So this is much special of it. Now, if you take the functor, which is left adjoint of this functor, then that will be the construction of the Stromcheck compactifications. So exactly the same way, if we take this forgetful functor from group to set, and if we wanted to construct a functor in the other directions, which will be the left adjoint in the sense that those two diagrams satisfied, then that construction will forces us to get the free group. And exactly the same way here, if we construct this left adjoint of this functor, that will be nothing but have this Stromcheck compactification. So the purpose of this adjunction is actually telling us that these mathematical objects like free groups, abelian adjacencies of a group, Stromcheck compactification, these are not only just a new mathematical object. All these has some very special universal property. So if you have similar type of object, then it can actually have some universal property it holds. So these are all special objects, and that's why it comes so naturally in a form of an adjunctions. So once we have this, then finally the growth-ending group. Growth-ending group is like here is also an example of a forgetful functor, but didn't forget everything. G is a functor from an abelian group to monoids, and monoids in another algebraic structure which we do not see often, and that's very interesting. And monoid should come just before groups. So just a quick remark how these algebraic structures actually we built. We start with set, no structure, then a set with a binary operation, no property, that's called magma. A set with a binary operation, and binary operation satisfy associativity. That's we call semigroup. Now a semigroup having this identity element, that's called monoid. And a monoid having every element inverse, that's called group. So this is the way actually we construct an algebraic structure based on another algebraic structure, which is a little bit primitive compared to this new algebraic structure. So in this functor, actually, it's an abelian group. So what did it forget? It forget these inverse elements, because identity is still there in the monoid by definition. Binary operation is still there, it is still associative, and this identity property is also holding here. So only it is missing a little bit of property. So forgetful functor doesn't always imply that it forgets everything and landed up with the underlying set. No, it depends on how much forget we need or how much it can afford to forget. So then growth-ending group is what? If we take a commutative monoid, because actually the general construction doesn't need to be commutative, but in growth-ending need to use it for the K-theory purpose, and for him it need to be commutative monoid. So if you take a commutative monoids and you wanted to construct a group from that commutative monoid, then this is again a very standard procedures, and one of the standard reference where you find this construction is this universal algebra book by P.M. Kohn. And one of the very first person who actually did this general construction from monoid to construct a group was actually Malser. So there are two papers, those actually not written in English, and I still didn't find any translation of it. But anyway, so this growth-ending group is nothing but the constructions of this left adjoint from these commutative monoids to this abelian group. Okay, so now we have a little bit experience with these categories and other terminology. And then almost at the end, let us talk about the second part of the category theory, in the sense that if you remember on the very first slide on the yesterday, we said that there are two levels of these applications of category theory. One is using on the set theory, and in some sense using in different areas of mathematics with respect to different mathematical structures. But also there are mathematicians generally called category theorists who actually study categories and try to give some axioms on different categories and then capture many mathematical structures. Now, you may generally say that why do you need such thing? Okay, the purpose is as follows: that we understood that every mathematical structure actually satisfies certain axioms and they forms a category. Good. Now imagine tomorrow we come across a new mathematical structure during our research, and we do not know whether product exists in that mathematical structure. But imagine that mathematical structure has been inside, instead of going inside that mathematical structure to literally see whether product exists or terminal object exists or direct sum exists or not in that mathematical structure. If we know already there is a certain kind of categories of which it is a member, and if that certain type of categories must have product, then that new structure should have product. So this is one of the advantage to unify or to organize different mathematical structure in different classes, such that each of them will have certain properties. So from that point of view, one of the earliest types of categories are Abelian categories. Examples of Abelian categories are these Abelian groups, K-modules, vector spaces, and Sanders-Maclane, Bushenham, and then Grothendieck are the people actually who contributed towards the development of this subject, as well as from the definition point of view. Actually, Bushenbaum was the first person who discovered or came up with this idea of Abelian categories, and later on Grothendieck reinvented and also readjusted it, and Maclane also did the same thing. And this Grothendieck definitions of Abelian categories is actually first appeared in his very, very famous paper in Tohoku journal, which now actually was in French, but luckily because of a mathematician, a category theorist, Michael Barr, you can freely get this English translation of this Grothendieck's paper. And if you translate the title of the paper, it calls Some Aspects of Homological Algebra. So that paper is actually one of the building block of homological algebra, derived functors, and as well as these Abelian categories. So there are still many, and also obviously Grothendieck spectral sequences, which is one of the most general spectral sequences what we see in homological algebra. So once we have these Abelian categories, then people try to start to further generalize it. And next generalizations is Quillen exact categories. And Daniel Quillen actually came up with this set of axioms on categories. So that means some mathematical structure should satisfy these axioms, and those categories will be called exact categories. Actually, although this category nowadays called after the name of Quillen, but Nobuo Yoneda, a Japanese mathematician, actually came up with all the ideas, and by somehow it didn't appear in the literature, and today we know it more like as a Quillen exact category. So this is another set of axioms. Then there is a bar exact category, the same bar what I was talking about, these translations of this Grothendieck's paper, Michael Barr. Then there is a protomodular category by a French mathematician, Dominique Bourne. This is much more recent compared to the other one. Abelian category is the oldest in some sense. And then there is something called semi-abelian categories. This is around 90s. Three people, George Analyse, Amartya and Walter Tholen from Canada. George Analyse is a Georgian mathematician. Semi-abelian category actually try to organize all group-like structures. Roughly speaking, group-like structure means if you take any mathematical or algebraic structure and if you see a group structure inside it, you can consider it as a group-like structures. For example, group is obviously such a candidate, but if you take ring, it has also a group structure. For example, with respect to addition, it forms a abelian group. Similarly, we can take vector space. It's also have a group structure inside because vectors, if you take as a set with an addition, that's actually an abelian group, and then we have action on this abelian group by this field. So these are the examples of group-like structures. So semi-abelian categories actually captured quite a number of mathematical structures from this axiomatic point of view. And after this, there is something called Nigerian forms. And this is not a typographical mistake of this initial G and Z. Actually, Z is Zurab Janalize. He's the son of George Janalize. And luckily enough, I was also a little bit part of construction of this procedure. And this father and son both are in South Africa in different universities. And this is one of the so far one of the most general axiomatic setup from the category point of view to capture many algebraic structures. And with using these so-called Noetherian forms, we managed to prove all isomorphism theorems just using from 5 axioms. And to understand those axioms, you literally do not need to know anything about category theory, and can be much simplified of that. And we are trying also to use it with homological algebra, and so far we also managed to prove all the diagram lemmas in homological algebra just using in this setup. And this setup has a special property that it's a self-dual. All the axioms are self-dual. That means if we have an axiom, the dual of it is also an axiom of the system. So you may ask, what's the advantage of it? The advantage of it that if we wanted to prove any statement, we do not need to prove the dual of it, because dual of it will be the free version of it. So a very simple example of is if we take this De Morgan's law. So we know that we can write this De Morgan's law with respect to union as well as with respect to intersection. So if we start to prove it from a self-dual axiomatic point of view, then we just prove it for one of this union, and then the other will follows by the duality. So we don't need to literally prove it again. So that's one of the advantages of it. So these are the roughly axiomatic developments in category theory. What we and people are still continuing working in these areas and try to organize and unify mathematics in roughly the sense what I talked so far. Of course, in these 2 talks, I didn't tell anything about category theory in details. As I mentioned, this is not even an introduction to category theory, but a pre-introduction to category theory, in the sense to tell you what is it this category theory all about and how it is related with this existing mathematics in different areas of mathematics. And if you are interested, of course, you can always study by yourself and can attend lectures and get books from there. And of course, you can look at the different areas of either from this point of view of category theory as an axiomatic development or as an applications of category theory as the other people did in the different areas of mathematics. So with this, the last a few references which I thought may be useful to you if you like to see different areas. Okay, so let me just scroll all together and then go one by one quickly. These are the few references, of course not exhaustive, and it's not true that these are the only references, there are other as well. Okay, so these are the few references in different areas of mathematics where you can see how successfully and inevitably category theory appears, and this functorial language or categorical language has been used. So algebraic geometry, of course, the first reference comes as Grothendieck's own work, because he is the person who actually introduced category theory in algebraic geometry and successfully used it, and his so-called best student, Delhi, successfully use Grothendieck's theory to prove this wild conjecture for which he received his Fields Medal sometimes ago. And there is another advantage of this categorical way of looking of this affine scheme. It actually generalizes of this taking this solution space of polynomials, not restricting on field, but we can take it on a commutative ring. And this actually opens the door of the use of these algebraic geometry tools to number theory. And that actually literally appears in this proof of Fermat's last theorem in this Wells work. Next standard book, which everybody knows in algebraic geometry, is Hastron, if not the most well-known book in algebraic geometry. And of course, Hastron also explained these notions of shapes. Of course, to express shapes, you need a functor, because shapes is nothing but a functor from category of open sets as a poset and two sets. So each of these open set, you just assign a set. And typical example is these continuous functions. So if we take a topological space X, take an open set, and for each open set, we can define set of all continuous functions, real value, for example, from that open set to real number. And that actually forms a ring. And this is nothing but the rings of continuous functions. So basically, rings of continuous functions is actually a shift from this open set category to this category of ring. Then the third one is comparatively new book, and I found it's very interesting. It has lots of adjunctions and very, very categorically written. Grothendieck's work still has not been translated into English, except I found the preface of EGA 1, which I mentioned in one of the slides before. And I myself do not know French, and also I couldn't read that one. So if you know French, or if you wanted to learn French, of course, this is the best reference in my opinion as far as algebraic geometry concept. But be warned that it's not a 300 pages book, because if you consider all the volumes, it will go to 8,000 to 9,000 pages of work, and that's what Grothendieck is. Next is algebraic group or Lie groups. One of the most standard reference, which is absolutely categorical with categorical way is written, is De Mazur and Gabriel. And Grothendieck himself actually mentioned about this book in his EGA 1. And it has also a little bit discussion of algebraic geometry and algebraic groups in terms of as a functor. And then the second one is actually freely available lecture notes on J.S. Milne's website. He has a series of lecture notes, very, very rigorous and well-written lecture notes, not only on these Lie groups or algebraic groups, in other areas of mathematics like Galois theory group. Maybe many of you have already seen. The last one is Waterhouse. This is a little bit older book, but also it's very down-to-earth book. It starts with matrices, general linear groups, special linear groups, and then from there it actually develops the general theory. For topological groups, in a very recent time from European Mathematical Society, this book by Stroppel has been published, and it actually literally computed the product, co-product, and many all categorical notions for these topological groups, as well as locally compact topological groups. For shift theory is now one of the indispensable tools in many areas of mathematics, as well as along with differential geometry. In fact, every differentiable manifold can be represented as a ringed space, which is a standard notation and standard notion of appearing in algebraic geometry, but this actually tells that how shift can be also used in other areas of mathematics, because as long as you have a topological space, and then you have immediately open sets, and if you wanted to study these open sets in terms of some algebraic structure, naturally you landed up with the concept of shift. So this book by MacLean and Mordek is not only a book on the shift theory, it's a very fantastic book where you can learn shift theory, one can get category theory, you can get a little bit of idea of algebraic geometry, and nonetheless, you get the whole idea of topos theory, which is actually been also invented by Grothendieck, which is the more general version of this concept of topological spaces. Finally, for algebraic topology, the most standard classic reference is Spanier. which in many places, I think in India, we follow this book. And if you open this book, you will see, if I remember correctly, the second chapter is about category theory. So it develops all the tools of category theory and then started to go there. And comparatively, we get a newer book, which is written by Dick, and it has represented these different constructions of these algebraic invariants, like fundamental group point, homologic group, homotopy group, all these in terms of functorial way. Because as we mentioned that in algebraic topology, what we are studying the functor between either top or homotopy category to this category of groups, and we assign these different types of groups associated with different this space. So this is all about what I wanted to say so far, and I think it's already 1 hour. Just 2-3 final remark about this, which is not only about technical things, it's more general, that the purpose of category theory is not to do an innovation over the existing mathematics. That is a very misconception, that category theory wanted to remove everybody from the world and change their religion and say tomorrow, okay, now all of you should do category theory. No, that's absolutely wrong. The purpose of category theory is to unify mathematics as much as possible, to simplify mathematics, to organize mathematics, so that many things what we did in different places maybe further can be easier way to see it and look it, and many of the connection which was not visible because of this constructional complicacy can be visible if we see it from the functorial point of view, from the adjunction point of view. And it is also absurd to expect that since it's a very, very high level abstract language, it will trivialize all the calculations. No, it is absolutely impossible. When we need to find the normal subgroups of a group of order 18, we literally have to calculate it. There is no way. But then what is this category theory is actually doing? Let us take a very simple example, that imagine we wanted to go from Agra to Kanyakumari, and we wanted to go by car. Then what we need to do, we need a map or road directions or a GPS. And category theory will guide you which way to go, such that you will not be diverted. But a GPS or a map cannot take you to Kanyakumari. You have to drive the car and fill up the tank whenever it's needed. So the process of this driving or the going is still need to be done. But if we do not know the directions, then what can happen that we landed up in Gujarat, and then oh no, this is not the Kanyakumari direction, so it should be on the other way. But if we have a lighthouse, exactly what lighthouse does to direct the ships in the old time. Nowadays we have this GPS as well. So since category theory looks mathematics from the top in some sense, so it is much easier to see the interrelations between mathematical structures, and maybe the same thing is happening in different areas and we are not aware of it because we are using different languages. It depends on what mathematical structure we are talking about. So if you like this type of mathematics to see interrelations and interconnections, how they are related with each other, then probably you like to further explore this area of mathematics. So it is not a separate kind of mathematics. This is mathematics. I mean, everywhere by these examples, probably now you convince that it's not a branch of mathematics itself. Of course, you can do research in category theory itself, but every mathematical structure is a category. So whatever categorically we do, it will have immediate applications or effect in some mathematical structure. So my opinion or my suggestion is, if you like to be open-minded, then maybe it is not so bad. Okay, so with that, just finally, if any one of you like to further contact me, so this is my university email address. You are most welcome to write me emails, and we can always talk. And that's the end of the today's category theory session. Thank you very much. Hello, yes.
Sir, please suggest me the name of the reference book for got things group in introductory level.
Group, right?
Okay, I do not know a specific book only written on authentic group, but since you asked, will it be fine that I will just have a look, one more search on this area and send it to Abhishek?
Okay, sir. Okay, sir.
Sure.
Is it all right?
Yes.
Okay, sir. Okay,
Okay,
sir.
sure. Thank you. Thank you.
Chintada, you want to say something?
Yeah. No.
Okay. Any other questions or? So I think there is Devasisda. Do you want to say something? Devasisda?
Thank you. Thank you very much, and I'm very much happy with the lecture. Thank you very much for the giving the lecture. I have no idea about the. I am working in physics subject, but I came to know there is another subject in category theory. And it is a fantastic lecture. Thank you.
Thank you so much. But just to let you know, in physics, there is a huge application of category theory.
Yes.
Specifically on this unified field theory, there are lots of people actually using category theory.
Yeah. There's the Lie group theory.
Yes, Lie group appears very naturally. Yes, you are absolutely right.
Lie group. Thank you very much for the very kind lecture. Very fantastic lecture.
Thank you very much. Thank you.
So if there is no other questions, so I would like to express sincere vote of thanks to Professor Goswami for his nice lucid presentation in pre-introduction to category theory. And I hope that we will have you again in our academic programs in near future.
Thank you, Abhishek. I will be always there.
Yeah, you should be. As a person from Burdwan, I demand.
Yes,
Yeah.
and your demand has been accepted.
Yeah. Okay.
This is our demand also.
Yeah.
Yes, all demands have been accepted with big thanks.
Thank you.
Yeah. So okay. So if there is no other questions or doubts or queries or any other introduction, so let me declare the end of this session, and we shall meet again tomorrow at 11 a.m. in the morning.
Okay. Thank you, Abhishek.
Thank you.
Stay safe. Yeah.
Abhishek, thank you.
Thank you,
Abhishek. ঠিক আছে
খুব সুন্দর ছিল।
Absolutely. হ্যাঁ
দারুণ।
খুব ভালো লেকচার হয়েছে, খুব ভালো, অসাধারণ। অসাধারণ।